Hi, this is Theresa Paulsen, one of the first Airborne Astronomy Ambassadors chosen to fly aboard the SOFIA aircraft. SOFIA is an acronym. The S stands for stratospheric. The stratosphere is the second layer of the atmosphere above the clouds and water vapor present in the layer underneath it. The O stands for observatory. The SOFIA aircraft is used to observe many different types of objects in the night sky. It has two advantages over the satellite observatories you might be more familiar with. It's much less expensive and it can be easily maintained on the ground, so it will last much longer. F represents the word for. For what? For the I and the A, of course. I stands for infrared. You know, heat. Infrared is a form of light with wavelengths just too long for the human eye to see. And A? You guessed it, A stands for astronomy. So together, that's the Stratospheric Observatory for Infrared Astronomy. Why do we want to see objects in the infrared? By looking at these infrared or thermal images of a boy and a cat, we can see a lot more than we can with our eyes. Infrared light can also pass through materials that visible light can't. This man has a bag over his hands. The visible light is stopped so we can't see them, but infrared light has no problem. The heat from his hands passes right through the bag. Infrared can also pass through much of the gas and dust in outer space, so astronomers can see what we've been missing. Case in point, this is the constellation Orion. On the left side you see it in visible light. Looks just like it does in the night sky, right? But on the right side is the same region in the infrared. Amazing, isn't it? The problem astronomers face is that infrared is trapped by water vapor in the atmosphere. In the graphic, you can see all the types of light trying to penetrate the atmosphere. Visible light, represented by the center yellow band, and radio waves, represented by the orange band on the left, are able to make it through to the Earth's surface. Just the longest microwaves are able to make it through, and thank goodness ultraviolet, X-rays, and gamma rays are blocked or we'd be in trouble. Notice the infrared, shown in peach, penetrates deeper but is still blocked. This makes the infrared a great candidate for an airborne observatory that can fly just high enough to gather most of it. In this graphic, the upper image demonstrates how much the infrared light is blocked by our atmosphere at ground level, and the lower image shows how much more we can see at 41,000 feet. Satellite telescopes may have an even better range, but they have a much shorter lifespan because infrared instruments have to be cooled with cryogens like liquid nitrogen or liquid helium, which are used up in a matter of a few years. SOFIA has just recently begun its science flights. Astronomers will use SOFIA to look at areas full of gas and dust, like distant galaxies, or the center of our own Milky Way galaxy. They'll look at the space between stars, known as the interstellar medium. They'll be able to look to see where stars are forming, how they form. They will also use SOFIA to learn more about planets, asteroids, and comets. So how does SOFIA gather infrared light? A Boeing 747 SP has been retrofitted with a rear compartment that holds a 100-inch reflecting telescope. Once high enough, the compartment door opens and the telescope begins gathering light. The SOFIA project has been a huge undertaking by the United States and Germany. Germany supplied the telescope and NASA supplied the airplane. Germany receives 20% of the flight time. Scientists from all over the world can propose experiments for the observatory in a competitive process. All of the data is later shared in an astronomical archive for anyone to use. I met SOFIA at the Dryden Aircraft Operations Facility in Palmdale, California. My visit began with the security office, where I signed and received my credentials. Once through security, I met many fascinating people, including folks in charge of the project. In this photo from left to right are Eric Becklin, Chief Science Advisor for SOFIA, Eddie Zavala, SOFIA Deputy Program Manager, myself, my partner teacher Marita Beard from San Jose, California, and Bob Meyer, SOFIA Program Manager. Before our flight, Marita and I had to attend a safety training. We learned how to put on our air masks and life jackets. We also learned how to use a radio in case we get stranded. This radio sends a signal for 64 hours that can tell searchers not only what plane you were on, but what exit door you used. Finally, it's time to head to the hangar and meet SOFIA. Next, we attended a mission briefing where everyone who went on the flight gathered to hear what the night would have in store. Our pilot went over the mission timeline and our flight plan. Then we heard from each of the scientists, Terry Herter from Cornell, NASA instrument scientist Jim DeBuser, and Oliver Krause from the Max Planck Institute in Germany. Now we're ready for flight. While everyone gets ready at their stations, let's take a tour of this magnificent aircraft. We'll start in the cockpit, which is not drawn in the diagram, but I bet you know where it is. Marita and I had to check it out. We even got to sit in the cockpit jump seats on takeoff. After takeoff, we headed downstairs to learn about what happens at each of the workstations. First up, Mission Control. Nancy McCown was the mission director for our flight. On her computer screen, we could see the telescope door open, much faster in this recording. Next to her was the flight planner, Ken Bauer. On his computer screen, we could see where we were, when we were about to turn, and how much restricted airspace was around us. Computer programmers were aboard this early flight to help with any issues that arose during the flight. They were there to write code to fix problems on the spot. Pretty handy. Toward the back of the plane, near to the telescope, is the telescope operator station. These folks were locking in on targets and monitoring the effect of turbulence on the tracking system. To their right is the scientist station. They scrutinize the quality of the images and process them to reveal the targets in their full splendor. This image of the center of the Milky Way galaxy was collected and processed during our flight. Pretty cool. In the very back of the cabin is the telescope instrument and counterweight. The telescope is so stable that even during turbulence, while we were jostled around, the telescope was still. Behind the pressure bulkhead is the telescope and cooling system. To detect the small amount of infrared or heat radiation from distant objects, the instruments must be cooled to 4 degrees Kelvin. That's negative 452 degrees Fahrenheit. The instruments are cooled with liquid helium to avoid interference from surrounding heat sources. Flying with the door open sounds a little crazy, but folks at NASA worked for a long time to be sure that the plane would be safe. They tested the design in a wind tunnel before it ever took flight. Initial flights then flew over the ocean, opening the door a little at a time. The engineered design has proven itself to be very safe and effective, so passengers can rest easy. Engineers who work on SOFIA's design have no easy task. The large plane needs to fly at very high altitudes for long periods of time. Our flight, for example, lasted about 9.5 hours, flying first east to maximize night hours. To get that high and fly for that long, they had to make the plane as light as possible, yet the plane has to carry a 17 metric ton telescope in the back end. That's as much as 3.5 full-grown male Asian elephants. All the while, the telescope must be able to remain steady, locked onto its targets. It's a massive object that sits on a pool of pressurized oil. Its own inertia and gyroscopic stabilizers help it to resist changes in motion. This design allows it to stay locked on a target the size of a quarter from 5 miles away, even through turbulence. The telescope must also be able to accommodate different science instruments. Universities and research groups around the globe can design instruments to process the infrared radiation. Infrared cameras are only one kind of instrument, and each is specialized for certain ranges of infrared wavelengths. Another type of instrument is a spectrometer that helps an astronomer figure out what objects and dust clouds in space are made out of. Each kind of atom gives off its own signature wavelengths that look like bands of light in the light spectrum. We looked at some pretty cool targets on our flight. A supernova remnant dispersing energy into space, a representative starburst galaxy, and a couple of Hilda asteroids thought to be just far enough away from the Sun that they might contain ice and therefore may be potential comet hybrids. And lastly, we looked at the center of the Milky Way galaxy to study star formation and matter as it encircles what is thought to be a black hole. Our mission ended with a debriefing. Everyone was pretty tired, but very excited to see the images that Terry Herder could share with us of that picture of the galactic center. What else will SOFIA discover? Only time will tell. You can be sure my students and I will be watching.